I would like to introduce myself first. My name is Dr. P. Amala. Actually, I have completed my UG and PG in the field of chemistry. I have done my UG and PG from Loyola College, Chennai. Then I just moved to this for my research purpose, the University of Madras. I have done in the organic synthesis research, especially in the organic functional materials, under the guidance of Dr. E. Kimogna Krishnans. And then afterwards, I have moved to this abroad for my higher research, especially postdoctoral research. I have done my research in various countries, Israel, Singapore, and also South Korea. Then currently, now I'm working as assistant professor in the Department of Chemistry, Madanapalle Institute of Technology and Science. In this particular lecture, I would like to give some small topic, that is nucleophilic substitution reactions. In this particular section, I would like to highlight the significant points, especially introduction, significant points, how we would like to solve some of the problems. So soon I would like to start my lecture. Now I would like to discuss about nucleophilic substitution reactions. In this particular discussion, I would like to discuss first introduction, second reaction, and third is the mechanism, and fourth I would like to discuss about the stereochemistry, and then is the fifth is the kinetics, and then factors affecting the rate of the reactions. So I would like to discuss the following points. The first one is an introductions. I would like to give some introduction about this nucleophilic substitution reactions. Then the reaction, I would like to discuss about this chemical reactions, and then what kind of mechanism it follows, and then talks about the stereochemistry of the particular reactions, and then what is the rate of the reactions, kinetics, and finally I would like to discuss about this factors affecting the rate of the reactions. So all this point I would like to discuss in this particular video. So first I would like to move to this introductions. So our title is nucleophilic substitution reactions. What is meant by a first is substitution reactions. A reaction in which an atom or a group of atom attached to a carbon is replaced by another atom. That is usually called as a substitution reactions. So before going very details, the nucleophilic substitution reactions. Substitution reactions can be classified into three types. One is this electrophilic, another one is this nucleophilic, another one is the radical. Okay, so substitution reactions can be classified into three types. One is electrophilic, other one is nucleophilic, and finally is radicals. But today we are going to discuss about only nucleophilic. But before going deeper into the topics, first we should know the basic concepts. What is electrophile and what is nucleophile? That is most important. Without understanding the electrophilic and nucleophilic, going inside of the topic is no meaning at all. So first I would like to discuss about this electrophile and also nucleophile. So the word it usually originates from the Greek word, actually. You can divide this word into two. One is electro, another one is a pile. The pile means it is a loving. And electro, it is just written as electron. So electron loving species are called electrophile. Okay. So electron loving species are called electrophile. Or in other words, when it loves an electron means it has a deficient in electrons. So in other words, you can write electron deficient species. So you can write it in a two different way. Either it electron loving species or otherwise it is an electron deficient species. That means electrophile, you can split the word into two. Electro means electron and pile means is a loving. Okay, so that means electron loving species is usually called as electrophile, or in other words it means it has a less electron, that's why it is going towards where more electron is there. So that is usually called as, otherwise it is called as an electron deficient species also. So you can see some examples here. Usually the carbocations, you can say all, or suppose tertiary carbocation is there. This is deficiency in electron, that is comes under the category of this electrophile. Okay, this is a charged, positive charged species, whereas in the case of neutral, you can write this BF3, boron trifluoride, or aluminum chloride. So most of the Lewis acids comes under the category of this electrophile because it's a lack of this complete of an octet rule. So these are some of the basic concept about this electrophiles. So the nucleophile, when it talks about, this is also, you can split into two, and nuclear means it's a nucleus, and then pile means is again is loving. On this particular definition, you can say electron rich species. Is usually called as the nucleophiles. So you can say this F minus, Cl minus, and bromine minus. These are all comes under the category of this nucleophile. Whereas regarding the neutral charges, you take a water molecule, there's two lone pair of electrons is there, and you take an ammonia, this is also a lone pair is there. So these are all comes under the category of the nucleophile because it has a rich in electron. Okay, it loves towards or move towards where electron is deficient more. So example of neutral species in the nucleophile is water, ammonia, and etc. Whereas when you take an electron rich species of this negative charge containing fluoride minus, chloride, bromide, iodide, etc. So this is the basic concept of this nucleophile and also electrophile. So our topic is nucleophilic substitution reaction. That means what will happen here? This means nucleophilic substitution reaction is a typical substitution reaction in which one of the atoms or functional group is replaced by the incoming nucleophile. That is usually called as the nucleophilic substitution reactions. Okay. There are various type of nucleophilic substitution reaction. Namely, you have an SN1, you have a SN1 and SN2, SNAR, like several type of the substitution reaction is there. Today, I would like to be emphasize or discuss about only the SN1 type reactions. The remaining reactions we'll see later in the upcoming videos. So first, I would like to talk about the SN1 reactions. So what is S stands for? S stands for substitutions, and N stands for nucleophilic, and 1 stands for unimolecular. I'll repeat again. The S stands for substitution, and N stands for nucleophilic, and 1 stands for unimolecular. So we already discussed what is substitution and what is nucleophilic substitutions, but the 1 is represents the unimolecular that shows the kinetics. That when the kinetics parts comes, I will discuss very detailedly. Now I would like to move to the reaction of SN1. Okay. First, when you example, I'm taking this. So tertiary butyl bromide, when it reacts with potassium iodide, the result will be tertiary butyl iodide plus potassium bromide. This is a typical SN1 reactions. Okay, I repeat again, the tertiary butyl bromide and reacts with this potassium iodide. The product will be the tertiary butyl iodide plus potassium bromide. This is the reaction of this SN1 actually. Then how this particular reaction works, what could be the mechanism for this, we'll discuss now. Okay. SN1 reactions, the mechanism, it involves two-step process. So it involves two-step process. The first step, it's nothing but this formation of the carbocation, and the second step is the nucleophilic attack on the carbocation. I repeat again, the mechanism of SN1 reaction involves two steps. The first step is the formation of a carbocation, and the second step is the nucleophile attack on the carbocations. The first one I'm writing. Take tertiary butyl bromide. And first step, the heterolytic cleavage takes place between the halogen and the carbon here. So thereby we will obtain the tertiary butyl cation. Repeat again. The first step in the mechanism. In the mechanism, the first step is the formation of carbocations. That means the tertiary butyl bromide, which undergoes the heterolytic cleavage between the halogen and the carbon, and thereby you will get the tertiary butyl cation here. This is the first step actually. The second step is this nucleophile attack on carbocation. So the second step is this: once carbocation is formed, the nucleophile attack on the carbocation, and thereby the product tertiary butyl iodide will be obtained here. So these are the two-step process which involved in the SN1 type of reaction, SN1 mechanisms. So now the question is, which is the rate determining steps among these two? So the question is now rate determining step. So we'd like to talk about this rate determining steps among these two. Among the two steps, the formation of the carbocation step is the slow step, whereas the nucleophilic attack in the carbocation is the fast step. I'll repeat again. The formation of carbocation is the slow step, first step, and the second step is the nucleophilic attack in the carbocation is the fastest step. So keep in mind always the slow step is the rate determining steps. So always the formation of the carbocation is the rate determining step. This is just like that in a running race, obviously. So suppose you have 5 athletes that starts running. So the last athletes, the completing the reaching the destination, then only the particular whole competition is finished. The same way, fast steps will always move very quick, but the case of whenever the slow step is completed, then only the reaction is completed. That is why the slow step is the rate determining steps. So in the case of an SN1 reaction, the first step is the slow step, especially the formation of a carbocation. That will be the rate determining steps. Since I already written a mechanism here itself, I would like to talk about this rate of the reaction so that it is easy for us actually. Now, I would like to talk about this rate now. So here, I already told you the first step, slow step is the rate determining steps. So the rate of a reaction is completely depend upon the first step of the mechanisms. So the rate is directly proportional to only the alkyl halide. Or in other words, in this particular case, exactly rate is directly proportional to tertiary butyl bromide. Okay. So the rate is here highly independent of the nucleophile. So that is very important one. So rate is independent of this nucleophile. Rate is independent of the nucleophile. So whenever you change the concentration of the alkyl halide, then the rate of the whole reaction is also altered. That is very important. Okay. For example, now suppose I am changing the concentration of alkyl halides. So rate equal to K into alkyl halide. Suppose if I am changing the initial concentration, that means the concentration of the bromide is doubled. Tertiary butyl bromide concentration is suppose is doubled. Obviously, the rate of the reaction is also doubled. Suppose if I changing the concentration is 5 times higher than the previous one, then the rate of the reaction is also 5 times higher, is faster, because the rate of the reaction is directly depend on the alkyl halide. But whenever you change the concentration of the nucleophile, since the nucleophile is independent of this rate reactions, I mean especially in the mechanism you can see it's a fast reactions. So whenever you change the concentration of nucleophile, it never alter the rate of the reaction in SN1. That is a clear meaning. Okay, so that's why whenever altering the concentration of bromide, then the rate will be changed. Okay, whenever you alter the concentration of the nucleophile, so there will be no change of alteration, no change in rate. So that you keep on mind. And one more thing you remember, in the beginning itself I told SN1 in that case abbreviation time, the one is nothing but unimolecular I told as a unimolecular. So uni means only one. So we look at the rate reactions. Here only alkyl halide only involved for the rate of the reactions. So only one substrates, not nucleophile. It's supposed to be alkyl halide and nucleophile will be involved. But in SN1, only altering the concentration of the bromide will change the rate of the reactions. So involve only substrates, not a nucleophile. So only one type, one molecule. That means that's why it is considered as a unimolecular. Okay. Whenever you consider SN2, suppose we'll discuss later, in that case, in the rate of reaction, both substrate as well as the nucleophile involved. That's why it is bimolecular, because both of them involved, especially nucleophile as well as the alkyl bromide. But whereas in the case of this SN1, only alkyl bromide is involved, nucleophile is not at all involved in the case of rate regarding the rate of the reactions. That is why it is considered as a unimolecular. So the kinetics is first order. That is the importance. Kinetics is a first order kinetics. So I hope you understand. So up to now we have discussed about these reactions and also the mechanisms of this. It involves two steps. One is the formation of carbocation and the very slow step, that is, and the second one is this nucleophilic attack and the carbocation. That will be the fastest step. So slow step is the rate determining steps. So regarding the kinetics, it is a first order kinetics because the rate of the reaction is completely depend on only the alkyl bromide, not depend on the nucleophile, because the first step is the slow step is the rate determining step. I hope you understand up to now. Now, I would like to move to the stereochemistry. So what type of stereochemistry products will be obtained in SN1 reactions? So first let's see that. Bottom. Suppose this is on the top side. So listen, regarding the stereochemistry of this particular SN1 reactions, suppose you are treating the alkyl bromide with an iodo compound, suppose. The first step will be the formation of the carbocation, as I told. The second step, the nucleophile attack and the carbocations. So there may be two possible formation of attack. Because the carbocation is a flat, is a planar molecule now. Okay, so it may be attacked from this top approach is one product, and it also attacked from the bottom approach, that is another product. I repeat again. So once the carbocation is formed, you may have a two possibility to attack because the carbocation is highly planar here. So the coming nucleophile, it may be attacked from the top approach, and also it may be attacked from the bottom approach. When it attacks from the top approach, obviously the product will be the retention of the stereochemistry, will be retention product. And whereas when you attack from the bottom, you'll be getting an inversion product. So you're getting both retention plus inversion, or in other words, simply, you'll be getting a racemic mixture. You'll be getting a racemic mixture. That means you get a retention and also inversion product. Okay, I'll repeat again. Keep in mind, regarding the stereochemistry, in the case of SN1 reactions, you will be able to obtain the racemic mixture. Okay, actually the carbon here is a chiral because it attached to 4 different groups. I'm talking about chiral molecules because that then only you'll be getting a stereochemistry product. If you do not have a chiral molecule, you may not get the stereochemical product. Only one product will be end up. So here, since it's a chiral molecule, this undergoes the solvolysis, suppose, using water or iodine. In these cases, as usual, the carbocation once is formed, then since it is a prochiral kind of thing, so once it starts attacking the nucleophile, obviously it may be end up with these 2 different products. One is retention and also inversion. The top approach is retention and the bottom approach will be inversion. So this may be, or in other terms, you can express it, it is a racemic mixture, both retention plus inversion product. It may be 60-40 or 30-70 or 70-30, depends. Okay, so this is the stereochemistry of a SN1 reactions. I hope you understand. Suppose you are getting, suppose an R, then it will be retention is R product and this will be S product. That's it. Okay. So racemic mix, in simple words, in SN1, suppose you're treating a chiral carbon, the chiral alkyl halides, treating this SN1 reaction, the stereochemistry product will be obtained. That will be a racemic mixture. It will be retention plus inversion product. That's it. I hope you understand this one. So next is the factors affecting rate of the reaction. So factors affecting the rate of the reaction in these cases. So first in this one, first point, nature of the substrate. I would like to talk about nature of the substrate. What type of substrates is most suitable for SN1 reaction? That is the question now. Okay, whether what type of substrate we can able to move very faster the reactions. So here I just shown the example only tertiary early. There should be a reason for that why I wrote tertiary. This is tertiary butyl bromide. Okay, the nature of the substrate which will be increase the rate of the reaction, it's completely depends on the first step, that means the mechanisms, the carbocation formation. Suppose you are taking tertiary butyl bromide, the end up will be the tertiary carbocation. Tertiary carbocation. If you take secondary, you will be getting your secondary carbocation. This is secondary carbocation. This is tertiary. This is secondary carbocation. And finally, you'll be getting this is primary carbocation. So if you just undergo the solvolysis of tertiary, you'll be getting tertiary product, secondary bromide, secondary product, secondary carbocation, and primary alkyl bromide, you'll be getting a primary carbocation. But now the question is, which is more stable, whether tertiary or secondary or primary? This is the question now. So as we all know that the tertiary carbocation is the most stable, and the next is secondary, and the final one is a primary. So the stability of this carbocation tertiary, secondary, and primary. So this will be the stability of the carbocation order. That is most important. The tertiary carbocation is the most stable, next is secondary, and then next one is this primary one. So as for the stability concern, tertiary is the since most stable. So most preferred substrate for this particular SN1 reaction is the tertiary alkyl bromide. Whenever you use this tertiary alkyl bromide, the rate of the reaction is very fast because the formation of the stable carbocation. So because since we all wants to live in the stable state, okay, we want a good money, good job and good money, live in a stable state. The same way the molecule also expecting. Molecule wants to stay in a very stable state. So the tertiary carbocation forms is very stable. So whenever you use the tertiary alkyl bromide, the reaction is the very fast. Okay, then is secondary and primary. That is why whenever you write SN1 reaction regarding the example also, kindly write only the tertiary substrate. Don't write primary. Primary bromides will not prefer SN1. It is mainly prefer SN2. We will see later why. But whenever you're recording the SN1 reactions, the tertiary alkyl bromide is the most preferred because it will form a tertiary carbocation. I hope you understand. So regarding the nature of a substrate, tertiary alkyl bromide is the most suitable substrate for the rate of to increase the rate of the reaction in the case of SN1. So this is the first point. So I would like to discuss one more aspect here. Suppose I'm taking the example of this one. Suppose I'm treating I minus. Most of the people write the product in such this way. This is what expected products people usually write. Okay, whenever this alkyl bromide, it is just treated with I minus, the replacement of the bromine will takes place and thereby the product will be obtained. But in reality, when you do the experiment, you won't get this particular product. You won't get this particular product. We'll see why it is. Because when you draw the mechanism, what is the first step? The first step will be the carbocation formation. Carbocation. So the first step is this carbon bromine halogen heterolytic cleavage will takes place and thereby you will be getting the carbocation. Okay. The next step is the nucleophile attack actually. Before the nucleophile attack itself, there is a possible of rearrangement. Why it is happening? This is exactly because of the last one we discussed the nature of the substrate, the stability of the carbocation. Now this is a secondary carbocation, but there is a possibility of forming this tertiary carbocation. That means you have this hydride shift, 1,2 hydride shift will take place. So that means this hydrogen will move here. Thereby you are getting a positive charge here. Next carbon. Okay. So here 1,2 hydride shift will takes place and thereby you are getting carbocation. There will be a rearrangement possibility is there because once it rearrange, it forms a very stable carbocation that is tertiary carbocation. Okay, as per I told, okay, we all wants to live in the stable state. The same way the molecule also expect. The molecule have a possibility to form a stable state from the unstable state. Okay, that's why the 1,2 hydrogen shift takes place, and the molecule now is comfortable. It is a tertiary carbocation formation is there. Now what will happen? Obviously, second step, the I minus starts attacking. That's the nucleophile starts attacking the carbocation. So this will be the product. So you can see now the expected, usually sometime blindly people will write the bromine exchange will be the iodine, that replacement, then this is the product they will write. But what will happen? It will not form as per the experimental result, because here the rearrangement take place. Rearrangement takes place. So it is very important. Okay. So why I discuss this particular point, because whenever you talk about the factors affecting the rate of reactions, which have seen the nature of the substrate. So the nature of the substrate tertiary is most preferred because of tertiary formation of tertiary carbocation, that is the most stable. In the same way, whenever you have this, suppose they given problems like that, how to solve this one, or what is the expected product, most of the time people write the wrong product because they forget the rearrangement here. That rearrangement is happening here, it is because of a stability. So once the carbon bromine halogen bond is heterolytic cleavage, it happens automatically. You have a positive charge here. This will be secondary carbocation, but there should be a possibility of forming tertiary carbocation. There should be a undergo of 1,2 hydrogen shift, and rearrangement takes place here. There will be a formation of tertiary carbocation. That is stable one. Then the second step, nucleophile will attack here, and because of that, you are getting this particular product, rearranged product. That is very important. Okay, here you are obtaining rearranged product. That is very important. Okay, and you may ask this, you can expect stereochemistry? No, because the reason is once it's rearranged, you can see this carbon is not a chiral carbon, because both methyl group will be there. That's why only one product. That is also very careful. Sometimes people may write this two products like retention plus inversion, because that is not possible here because of this both the carbon which is rearranged, then the carbocation, which the carbon which having a cation that have both methyl group, it's not a chiral here. So that's why only one product is just not like a stereochemistry product here. Okay, so I hope you understand. So many times students, be careful, because sometime when you address the problem of SN1 reactions, there may be possibility of a rearranged product will be there. So we have to be carefully analyze everything. Okay, so be careful. Same way, you can see one more problem if you just possible. Now you can see that actually. In this cases, you have this problem cyclohexane based. Okay, suppose this when you undergo solvolysis, suppose you have a water molecule I'm taking now. So first step, as usual, you will be getting carbon bromine bond will be cleavage will happens, you will be getting a positive charge. Here also you have to look at whether it is there any possible to undergo rearrangement so that the molecule will stay in a very stable state. Okay, now it is a secondary carbocation. Okay, now if you take 1,2 methyl shift, just move here. So what will happen? You just take here positive charge. Now you see this, the carbon bearing positive charge, now it is a tertiary carbocation. It is a stable one. It's a tertiary carbocation. So that is, now this tertiary carbocation will react with this water molecules, and thereby you will be getting Now deprotonation will take place. Now you are getting the product. So here rearrangement takes place from secondary carbocation to the tertiary carbocation. Then the second step, obviously nucleophile will attack here and thereby the corresponding product will be obtained. But one more thing here, the product you written here, you can write it in the racemic form because here this carbon is a chiral carbon. So you can write in both the way. Plus and also that's all. So it's a racemic mixture. So racemic mixture is a product. So I hope you understand. So whenever you solve the problem, you must be careful enough whether it is possible to undergo rearrangement or not. If it is not possible, no problem. But if there is a possible to undergo the rearrangement from secondary to tertiary, you must do the rearrangement and then only the second step starts to react. That means the nucleophile attack. Okay, then you have to see that carbon is a chiral carbon not. If it's chiral carbon, the racemic mixture will be product. Otherwise, you won't get a racemic mixture, you will be getting as a single product. So, but in this case, you'll be have a possible to get a racemic mixture. I hope you understand this particular problem. So this is I discussed because nature of the substrate, that's very important. Okay, tertiary is the most stable, secondary and primary. Okay, so in a detail, if you see the nature of the substrate, till more, I'll write the clear order. First is tertiary benzylic and then tertiary allylic. And this next talks about this secondary benzylic and then this is secondary allylic. This is tertiary carbons. Tertiary carbon. Now, this primary benzylic and then secondary carbon and then is primary allylic. And next one is the primary carbon. And next one is a vinyl. Next one is a phenyl. Next one is a methyl. So this is the order. Okay, exact order of the reactivity regarding the SN1 reactions. First one is tertiary benzylic and tertiary allylic. If you have tertiary carbon and tertiary benzylic, obviously tertiary benzylic will be the most preferred because of the resonance. There's no question this one. Okay, when you talk about this tertiary benzylic, CH double bond C, R and R. Okay, suppose you are taking this one is it's a positive charge. Okay, so you have to be careful. So when you talk about this benzylic, it is tertiary benzylic will be there, and you also have this tertiary allylic. That is also important. Okay, so when you write allylic CH2 double bond CH, C, R and R, this is a tertiary allylic. Okay, tertiary allylic will be there. So very careful, both of them R group will be there. So tertiary allylic is the most stable as compared to the secondary allylic. Okay, so it's all about this. This is the order. It's all about the stability. Even when you talk about tertiary carbocation, is also it's why it is most stable when you discuss means you have a 3-methyl group. It's electron donating groups, so that will stabilizes the carbon here. That will stabilizes the carbon here. That is why tertiary will be the stable one when you compare to the secondary one. Or in other words, it's a more hyperconjugative resonance. You can say 1 plus 9, totally 10 hyperconjugative resonance will be possible. Okay, that's one of the reasons why tertiary is the most stable than the secondary, and the secondary, I mean, more stable than the primary. When you write the secondary, obviously 1 plus 6, original structure 1, 6 you can write resonating structure, totally 7 hyperconjugative resonance is possible. And similarly, CH3, CH2 plus, if you write it 1 plus 3, it is a 4 structures. Okay, 4 resonating structures you can able to write it. So that is detail. If you go, we can see, but currently I'm just talking about why this is most stable tertiary, secondary, and primary. Moreover, the methyl group is the electron donating, so that will stabilizes the carbocation. So keep in mind, and this is the order of this reactivity regarding the SN1 reaction. The tertiary benzylic and tertiary allylic almost equal reactivity. But when you compare with tertiary carbon, this is more because of this. Obviously, you have a resonance formation is possible, is there, like this. So that is a reason. Okay. So generally, in UG level, you can more understand about tertiary, secondary, primary. That's more than enough. But when you go higher and higher, you should have the ability to explain tertiary, benzylic, allylic, and vinylic in all these cases. So, but this is the order of reactivity regarding the substrate in SN1 reaction. I hope it's clear. So I repeat again, tertiary, benzylic and allylic, similar reactivity when compared to this tertiary carbons. So next one is secondary benzylic, secondary allylic, and tertiary carbon. And the next one is primary benzylic, primary allylic, and also this is secondary carbon, then primary carbon, and afterwards vinyl, phenyl, and methyl. Methyl is this almost the least reactivity consideration in the case of this SN1 reactions. Okay, this is regarding the nature of the substrate. I mean, reactivity, actually, how reactivity will be varied based on the nature of the substrate. Next, just talking about this nature of the leaving group. So first one, we have seen how the nature of the substrate affects the rate of the reaction in SN1. And the second one, we are talking about nature of the leaving group. Okay, you know this alkyl halides, you have an iodide, okay, bromine, and then is chlorine, and then fluorine, chloride, iodide, bromide. So regarding the alkyl halide, when you talk about regarding the alkyl halide, Ri will be most reactive, considered RBr, and then chloride, and then fluoride. Okay. So whenever alkyl iodide will be there, similar type of substrate. Suppose you take this alkyl bromide and alkyl iodide, probably alkyl iodide will be fastest, because the reason, obviously, the iodide has this better leaving group because it accommodates more positive charge since the bulkier group. That is the reason. So iodide will be reactive faster than the bromide. Similarly, next bromide will be reactive than the chloride, and the chloride will be reactive than the fluoride. So this is the order regarding the nature of the leaving group. So whenever you have an iodide compounds, alkyl halides, the rate of the reaction is fastest compared to this. You have a fluoro or chloro. Okay. So because this iodide is a good leaving group, it has accommodate more negative charge. Since it's a bulkier molecule, it accommodates more negative charge on that one. So that could be the reason. So whenever suppose they ask to arrange the order of the reaction, reactivity, you must see whether if it based on the leaving group, then you must be understand, okay, whether how it can be affected, whether it iodide is there, or alkyl iodide, alkyl bromide. We just start comparing because obviously iodide will be most reactivity as compared to this bromine because of the leaving nature. This is the second one. And the next one is this, is an very important nature of the solvent. So next one is we talk about the nature of the solvent. So an SN1 reaction and what type of the solvents are more suitable. Okay, most important is this polar solvent and protic solvent. Polar protic solvent, it is highly compatible. Polar protic solvents is highly compatible. So what is a protic solvent example now? Take water molecule, ethanol, and also acetic acid. So these are all protic solvent. It means, what it means, protic solvent, a molecule or species which able to donate H+. That is usually called as a protic solvent. And that solvent is highly polar in nature, then it is called as a polar protic solvents. Okay, my question is now, why polar protic solvent is most favored for SN1 reactions? The reason behind this, whenever you look at the mechanisms, the first step is the formation of the carbocations. I hope you understand. No? So carbocation is there. So when look at this water molecules, you have this oxygen atom have two lone passes there. That lone pass will able to interact. I mean, it has a dipole-dipole kind of interaction so that it stabilizes the carbocations. That is the main reason. That is why obviously polar protic solvents will favor this mostly in the case of this carbocation formation, the SN1 reaction especially. Polar protic solvent is most favored for SN1 type of reaction. For example, if you write this carbon pluses, so when you have this water, it's a delta minus, obviously. So you have a slight interactions will be there. This is a delta plus actually. Delta minus, and then so whereas you have this water molecules will be reacted here. H plus, and then bromine is delta minus. So whenever you have this polar protic solvent, okay, the bromine which have this interaction of this with hydrogens, obviously the carbon bromine will try to be facilitated to be cleave faster, and as well as this carbocation which has the dipole interactions with this lone pair and the oxygen, especially polar protic solvent, that will able to dipole-dipole kind of interaction. It stabilizes the carbocation is also. That is why mostly in the case of this SN1 reaction, polar protic solvent is most favored to increase the rate of the reaction in SN1. So that is the main concept. It stabilizes the carbocation. Okay, that's why the polar protic solvents plays an important role regarding the nature of the solvent. Okay, I hope you understand. So the factors affecting the rate of reactions, first one is the nature of the substrate, and the second one is this nature of the leaving group, and third one is this nature of the solvent. In the case of a nature of the substrate, tertiary is the most stable than the secondary and the primary. It is due to the stability of the tertiary carbocation. Because of this, more hyperconjugative resonance is possible in tertiary carbocation. Whereas in the case of nature of the leaving group, obviously iodide will be fast leaving, good leaving group, because it has accommodated more negative charge since it's a bulkier group. That is the reason. And then that's why when you have an iodide compound and bromo compound of alkyl iodide and alkyl bromide, obviously alkyl iodide will be reactive faster than this bromo compound. And similarly, when you talk about this nature of the solvent, obviously polar protic solvents will be highly favored, regarding the SN1 reaction, because the carbocation formation, it's stabilized by this, the polar solvent, the dipole-dipole interaction takes place. That is the reason, especially the polar protic solvent is highly favored in the SN1 reaction. Okay, I hope you understand in SN1 reaction is most of the part. Okay, so better, especially you should have an ability to solve the problem of an SN1 reactions. Okay, because most of the time students understand organic chemistry is a bit tougher. It's bitter in taste for them because of the reason is they just memorize it. If you memorize, it doesn't work organic chemistry. You must understand the concept, especially you try to solve those problems. Okay, when you try to solve the problems only, you start to apply the logic behind this, what type of reactions, then only you should understand the concept and you should understand really what happens in the chemical reactions. Okay, so today we have seen SN1 reactions. What is the introduction about this? Okay, what is a substitution reactions? What is nucleophilic substitution reactions, etc. We have also talked about what is electrophile and is also what is nucleophile. All these things we have discussed. Okay, and then we have also discussed specifically SN1 reaction. Okay, S stands for substitution and N stands for nucleophilic and 1 stands for unimolecular. That means one is talks about the kinetics, it's a first order reactions. So SN1 reactions, usually alkyl bromide, alkyl halides generally reacts with this nucleophile and the corresponding product will be obtained. So regarding the mechanisms, I can say that we have already seen clearly there are two steps involved in SN1 reactions. The first step is the formation of the carbocation and the second step is the nucleophile attack on the carbocation. Among the two steps, the formation of the carbocation is the slow step, whereas the second step, the nucleophilic attack on the carbocation, is the fastest step. So among the two steps, the slow step is the rate determining steps. Okay, so whenever you talk about the rate of the reaction, the formation of carbocation is the significant one. How fast the carbocation is formed, that the reaction will be finished. Just like as I told, in a competitions, usually in athletic competition, when the athletic will finish, usually the last person also should reach the destination. Similarly, same way, the slow step that has to complete, then only the reaction is completed. So the second step, the slow step, is the rate determining steps. And also we have seen about the stereochemistry. Regarding the stereochemistry of the SN1 reaction, the racemic mixture will be the product. Whenever you subject the chiral molecule for SN1 reaction solvolysis, obviously what will happen? The racemic mixture will be the product. That means you will be getting both retention as well as the inversion product. The first step is the carbocation is formed. It is a planar molecule, so that the carbocation which attacked by the nucleophile from the top approach as well as the bottom approach. Usually the top approach will be a retention product and the bottom approach will be an inversion product. So this will be a racemic mixture. It may be 60-40 or 30-70 and etc. So stereochemistry concern in SN1 reaction, it is a racemic mixture. Okay. And next one is factors affecting the rate of the reactions. Obviously, you understand, one is the nature of the substrate, and the other one is the nature of the leaving group, and other one is the nature of the solvent. The nature of the substrate, tertiary, secondary, and the primary, and the nature of the leaving group, iodide is most reactive than the secondary, and iodide is most reactive than the bromine, and bromine is most reactive than the chlorine, then chloride will most reactive than the fluoride. So this is the order. And whereas regarding the nature of the solvent, polar protic solvent is the most suitable for SN1 reactions. These are the main significant points in SN1. And apart from this, we have also discussed about the rearrangement products. That is the most important. Students many times is failed to give the correct answer in the rearranged products only, because where there is a possibility of forming the most stable carbocation, if there is a possible to undergo rearranged product, then obviously you should write the rearranged product. First you have to check, once the carbocation is formed, first step, is there any possible to undergo rearrangement so that the carbocation will attain the stable carbocation. If there is a possibility, we have to rearrange the product, rearrange the carbocation and write the stable form of carbocation, then the second step of nucleophile will attack them. I hope there are many problems based on this rearranged one. We should be always careful. Okay, I hope you understand. These are the point I have discussed in SN1 reactions. I would like to discuss SN2 later in the upcoming video. Thank you very much for your kind attention and watching this video. Thank you. Thank you all.